Nice to see you again. It has been a week, isn't it? So did everyone have a good weekend? Were you celebrating that not seeing me, or you're really sad not seeing me over weekend? Well, either way, it's a nice turnover, and I'm glad to see you again here in the class. I have some news to break. The first one is not so good. I have to be frank with you. My health was compromised. But I promise the teaching quality will not. Actually, in this particular lecture and in the following consecutive 2 lectures, which I will lead, I prepared freshly new materials. And these new materials are so new that they did not exist in the current IC data repository yet. And many of them were so new that it's also first time I worked together with Giuseppe on these topics because we think they're important. So I want to guarantee with my best capability, I'll present the best materials for you in this class. And due to this little change with my health status, I also want to present a new approach. Last time we had a talk basically using Zoom application. We have slides, I talk through, and many of them responded. However, I found it's a little challenge for me to perceive your reactions. So most time I just talk in the screen. It doesn't give me a real-time live feedback, which is really not helpful for me to understand the status of the class, especially the material I present in the class a little more rooted in the nature of mathematics. So I realize it's become important for me to understand you, where you are, and how we can move in the same space, hopefully together. So for that, I present a new approach. There's a little board here, as you see. I will use the chalk and board to write down things together with you. I also limit my space. See, I'm not using so much space I have in the slides where I can be so luxury with the space to produce all kind of equations I want. I realize many of them may not enjoy them as much as I like to do. So I also limit my space. I actually have EU here. Do you know what EU means? It means eliminate the unnecessary so that necessary can speak. So I'll try to condense my words and my key material on this small board together with you. Of course, I may have to erase a few times as we progress. So that's the new approach I want to present to you. And also, I want to address one challenge, which I heard from some of you, is about the mathematics. I don't know, everybody's feeling about the class in the last one, also including the interpolation, Fourier transform, which was one lecture before. How do you feel about the materials? Some of them were feeling the math part may be a little challenging. Well, I would argue in this way. Just imagine when you started the class, you didn't know much about Linux environment. Many of you may not even have a good exposure with Python coding. So far, if you look at yourself, you already achieved much more than what you were in the beginning. So it just takes time and practice for you to move forward. So that's with mathematics. If you think math is difficult, try to be more difficult than math. If you think math is scary, try to be more scary than math. Actually, I want to be honest with you, mathematics wasn't meant to be that way. It's trying to be simple, clear, make things explainable and understandable. So that's why I want to do this together with you. Hopefully, we can reach a mutual understanding. So if you still feel, this is a challenging activity, I recommend to think a hero in your life that you think is great. I don't know, Napoleon, who was beaten up when he was a child, and eventually become a worldly admired general in Europe, and eventually almost conquering entire Europe. Or Alfred Wagner, who proposed that Africa and South America can be fit together, and during his time, nobody believed him. Or if you like Michael Faraday, who talk about electricity and magnetism are the same thing. And also during his time, nobody really believed such things can happen. So you have to believe yourself. If you want to climb up the mountain that you think you can, your task is to achieve it. And the first step is that you have to believe in yourself that you can achieve it. You have to find the courage and the motivation to achieve the goal. So I recommend you to find the purpose to the class. And I want to present is the way to build, brace, and defend your argument. So the part I lead is not about delivering a solution. It's because no solution is the best solution, because there's always a better solution. What I want to emphasize is your decision, because there's no decision better than your decision, and your decision is the best decision. So it's the process I want to work with you and share with you my experience, how to think and analytically, critically on the literature, on the existing paradigm of geoscience, and try to identify a particular point for yourself. I believe by this point, you can find the libraries, you can find the code by yourself. So I hope we can talk about something even higher, at a higher level. Einstein's once dream was trying to develop one equation to capture the fundamental principles that governs the entire universe. Of course, I'm not that ambitious, so I use a little board trying to demonstrate. I'm also thinking simple is beauty, and let's try to achieve this goal and do this activity together. If you remain thinking, what I do may not be the bad thing you want to do, you just enjoy doing some existing code, that's your decision. I respect your decision, and you can make better use of your time. That's totally up to you. But I just want to tell you before, if you want to turn off the camera, that my material has an inherent logic. So if you don't catch up in this one, it's less likely you'll catch up in the next one. Yeah, so with that, I would just finish up my little speech in the beginning. I hope you'll be with me together to challenge these new materials, but I promise you these new materials will be beneficial for both sides. Okay, so about the course plan. I will have 3 lectures, as a main player, 3 lectures, today, Thursday, and next Tuesday. So basically today, I will lay out some fundamental probability and statistical theories for the sake of a conversation in the next 2 lectures. In the next lecture on Thursday, I will more or less focus on something called the species distribution model, because many of you explained to me this is a very interesting subject, especially those are from the discipline of ecology. To me, it's nothing else than just another kind of equations, but I'm happy to talk about it. But before we move there, we need to build up our vocabulary, and that's pretty much the purpose today. And the next Tuesday, we're going to focus on some case study, which is prediction of tree height. And Giuseppe had spent a lot of time and effort to carefully prepare a wonderful case, which has a very rich context. And I will work together with you, primarily using random forest as a method to demonstrate this case. So that's pretty much the layout of this 3 lectures I'm going to lead. And today I'm going to talk more on the fundamentals. Now, before I move on, does anybody have any questions or suggestions or objections at this point? Okay, well, at least I can see you from the screen. That's really good. Somebody already smiling at me. Thanks so much. I really appreciate it. So let's do a recap. So last time we talked about uncertainty, especially conditioning, right? So I just try and talk with you together, you also can refresh your memory. We said that there are a lot of errors in the modeling activities, especially in geoscience and also in many other areas. And these total errors can be broken down into 2 parts. One is a computational error, and the other one is a data error, right? For the computational error, we pretty much capture the concept of machine precision. I hope this is going to work. Let's try if you can see. Right? The machine precision. What is a machine precision? Anybody still remember? It's a beta 1 minus p divided by 2, right? And why we have this? Because the numbers in the computer system are presented in a discrete way. And we use something like scientific notation to represent all the real numbers in the computer system. And in this particular representation, we introduce this concept P, which is the precision of your representation. And this particular quantity matters because it will propagate as you perform some analysis and operations. And this one will represent itself in the level of representation. So some numbers in the binary system themselves cannot be represented precisely. If you remember in our toy example in the last lecture, there are some fundamental equations we agreed on, but due to the imprecise presentation, the error propagates. Additionally, this one also going to manifest itself at the operational level. When you perform addition, reduction, multiplication, all these kind of operations, you can think mathematically can be precise, but when you leave the job of the computer, they carry on the errors. So all these will contribute, could be significant amount to your total error analysis. By the way, I updated the lecture notes from the last class. If you download it before the end hour of the class, you may want to download again because I realized some typos. I made corrections and re-uploaded it. Nobody told me from you that you have discovered typo or something. If you did, please let me know. I'd be good for everyone. Okay, that's just a computational error. Then we talk about the data error, which is a bigger part of the lecture last time. So we talk about how to ask a question. The question need to be well posed. The conditions the question to be well posed, right? So what conditions are if the question are well posed? Anybody still remember? There has to be an answer. So the solution has to exist and the solution has to be unique. Also, the solution has to depend on the data continuously. It's a very rigorous and strict condition. Many times in the real life, we may not meet that condition. We still have to work out a solution with a real life problem. Then we talk about solution, right? So even though sometimes the question was not well posed, we hope the solution should be well conditioned. So what that means? That means if you identify a solution, and that solution should be produce the outcome numerically on the similar magnitude in terms of uncertainty with respect to your data. So in other words, you need an approximation. So we have to live with approximation. You can probably develop a closed form, precise mathematical solution to a problem, but in your real application, due to the issues with the numerical representation, due to issues with the data uncertainty, you have to approximate one way or another. And this approximation means your solution will unlikely to be the true solution, but it'll be good enough if you find a nearby solution, right? What it means, if the nearby solution, I hope you can still see, it's not too far away from true solution, and you compare that one with your input data, and this one is near to 1, then you should be satisfied. This is the condition you should ask yourself if you can meet for this particular solution, right? If your input data just have a small change, then your solution change exponentially, astronomically. That means you have looked at the solution more or less, because you always have uncertainty in your data. So that's the fundamental idea of this called conditional number, right? That's the basic definition. Now, from here, we move into 2 particular examples. I think I have to erase here because I have no more space. One is a linear system, one is a least square system, right? In the linear system, we said the condition number is what? Is the matrix norm multiply the inverse of the matrix form norm, right? And in the least square system, it's very similar, but we have to construct a so-called pseudo inverse matrix, because the matrix itself may not be inversible. I will not lay the equations here because it will be a lot of writing and the board is not dry yet, but I just want to draw one particular point to your attention, because many of you are more graphically oriented, and also I think this is very good representation. In the least square system, what you have is something like this. So this one is y equals to ax. This r equals to b minus ax. Yeah. So if you think about least square, which is we do more time in linear regressions, you are trying to find a particular solution here where b is your response variable. This A is your matrix. In term like geoscience, like you make a table, you have rows and columns, that's your table. And X is your solution, is your coefficient you want to get. Because the system is overdetermined, what that means? That means you have more rows than columns. Maybe you have only 10 coefficient, but you have 1,000 data points. So with the overdetermined system, you want to find a solution in this space. You do a projection. And this particular projection will make this response variable to approximate to the true solution, which is y here. You don't know, by the way, on this particular plane. And this is right angle perpendicular. And this theta is pretty much corresponding to the residual we talk most time. So the smaller theta is, the smaller residual is. And we also demonstrate that this is only useful if you have both small condition number and small residual, and you can assess the stability and the reliability of your model. And I think last time, we also left some questions or provocative thoughts in the lecture notes. I just leave here, pause here for a few seconds in case anybody made an attempt or you want to discuss some questions. At the same time, I will erase the board to prepare for the next part of this talk. Anybody work out any problems? They're not so interesting in the lecture notes. Let me just shift this view a little bit to see somebody else who is what. Okay.
So
well, it seems to be.
You can review the question that you posed last time.
Yeah, there are several questions, about the projection matrix, whether the identity matrix can be a projection matrix. But if you haven't worked on it, will be enough, probably to think about right now. But anyway, it's not a problem. It's your interest. It's your interest is the primary thing. If you don't think that's interesting you, it doesn't really matter. I'm going to move on to the next one, and hope everybody did it. I had a reading assignment, which is a paper. I asked everyone to read about it and think a little bit about your feelings and everything. So that's a paper. It's titled, what's the role of a hydrologist in the era of machine learning. Actually, that's one of the papers Giuseppe recommended me a long time ago, and one of the papers I really quite enjoyed. So I'll take an initiative to explain a little bit about the background and my idea, why this paper, and what's the key point from my angle. First of all, some of you, it's a paper written by hydrologists. Many of you I knew are not hydrologists. You may wonder why this paper, why I have to read this paper, why this paper concerns me. Well, if you have read the paper, you will realize, although it was mentioned like hydrologist, but majority part of this paper was pretty much at level of geoscience. It's very broad. It has a very high level conceptual picture for the current status of geoscience. And that touched on the point of the nature of interdisciplinarity of geoscience. Look at people here. We have biologists, ecologists, geologists, social scientists, software engineering, and all of you have your own technical background, and you all come to try to attack some geo problems. So it's a nature of interdisciplinarity. So that angle, I want you to read this paper, and in particularly, I want to point out a few points in the paper that I feel is relevant to my personal experience and relevant to the point that this paper can be quite useful to you. So let me just grab this paper. If you still have it in your hand, there are not many equations. There are equations, I think, on page 10. So there are 3 equations. I'm not trying to explain all these equations, but if you look at the format of equations by itself, they're very general. They are written in a very general format. And some of you who practice like spatial epidemiology, evolutionary biology, of course, me, chemistry, when you look at these equations, it resonates immediately. So all these equations contains information about this particular phenomenon you want to model, but they change a little bit in different fields. So that's why I try to explain how I was able to move between different fields and see connection with them. And that's also why I feel I want to make a promise that I want to get everybody in class to be included. We have a very diverse group. I don't think you expect me to speak psychology, economy, everything. But if we speak these equations, we are speaking on the same page, right? So these equations have the same root in mathematics, but they have different variations in a particular field. So that's the point I want to make here, and why I think it's possible for me to include everyone in the class. Now, I want to go to the content of this paper. So there are several points of the paper I want to highlight with you. Hopefully, you may see the value as I do. So the first one is the Bevan's cloud. So that's in the introduction part of the paper, where the author mentioned that the two-cloud speech, which came from physics, right? So if I read the paper, you realize that in the development of physics, there was a bottleneck point when people realized or believed the classical physics can answer almost everything. But there are two exceptions or outliers. One is the ultraviolet catastrophe, and the other one is the Michelson-Morley experiment. And each of them eventually developed into a big subject in physics. One become the root for quantum physics, and the other one is a theory of general relativity. So what this means, you see, as a data scientist, we talk about data and the hypothesis, right? So that's pretty much the framework we do in science. Now, if you have data to support your hypothesis, and people say, you got a measurement. If you do not, or you discover an outlier, you make a discovery. So that's the key I want to convey, the key message I want to convey with you, is that this exceptional phenomenon may be the root of a greater discovery. And the author actually using this particular analogy to say there are something like this, two particular phenomena still not resolved in the field of hydrology. Maybe I can argue this not only in the field of hydrology, it's pretty much covered the entire geoscience. One is scale, the other one is uncertainty. I think uncertainty is not something alien to us. We already talked so much last time. So I will not put too much time here today to talk about uncertainty. But I want to talk about scale. Now it's a question to you. So what's your understanding of scale as a geoscientist, ecologist? What do you mean the scale? What is a scale?
I think it can be different things, but usually we consider it like the level of details at which we study a system.
Yes, I agree. But I think that's perfect. But that also ties to the level of details, right? That's exactly the scale we talk about. How much detail we consider the detail enough. So scale, in my personal view, is such an important topic. There are numerous models effort trying to address this one, and I'm going to point out one particular example later in this class. But just before that, let's just hold on. Let me talk about the last thing this paper emphasized, which I also think is important. It's about directional suggestion. The paper mentioned theory-guided data science. So the challenge of data science versus the data-driven approach versus hypothesis-driven approach is that traditionally, when we have the hypothesis-driven approach, we iterate between data and hypothesis. And once we have reached a certain level, we condense those hypotheses into knowledge, and we can build on top of it. But in the data science, our end goal many times is so-called actionable models, which has particular purpose. Most time it's predicted purpose. But this is not perfect, because many times the data were imperfect. They may misrepresent or underrepresent the physical reality. And in our words, we call about supervised learnings, but you have to have a good supervisors. If you don't, then your model may not be in the right direction. And the other one is interpretability. So many times our model is so good, can predict good performance, but it's very hard and challenging to interpret. So the author argue that there are some strategies you can combine data science and the theory. So one thing I want to show here, which is not dry yet, but I can probably help it a little bit. So the data science modeling, the central task, it's pretty much a match between data and your model in the space of complexity. If I divide this space into 4 parts, if you have data highly complex and your model couldn't catch up, you have underfitting. If you have data that's simple enough and use too much complexity in the model, you are likely to get overfitting. And our goal is trying to find the path in this diagonal direction. So that's one particular use of theory to guide you for choosing the right family of math models to build a reaction, to build a particular applications. For example, I think this one people are all familiar with. So if you can see here, I say G is a function of expectation value of Y equals to X, B. X is a matrix, B is a measure X beta, it's coefficient. So what is this? It's a generalized linear model, right? So in the framework of general linearized models, you have to choose this G, it's so-called link function. And link function have several possibilities, can be identity, can be logic, can be log functions, and that branch into logistic model, Poisson model, or even just regular regression. So depending on data, you have to choose the level of complexity of your mathematical framework to address this problem properly. And the other one actually that's in the paper, where you can see is on the figure 7, where the author demonstrates a particular application neural network where you can apply the physical rules to constrain the activation function. So I believe later on we'll talk about this particular neural network structure. I think Antonio will lead through that. I will not dwell too much, but I think my point is here is basically demonstrate the 2 key concepts this paper trying to show you and the potential direction. So now let's go back to scaling, the scale, okay? So I will use an example to illustrate this concept of scale. Let's use an example in the field of a species distribution model. Can anybody help me to explain what is a species distribution model, just for those who are not in the field of ecology? Can I just use some simple words to capture the meaning of a species distribution model?
Well,
Anybody volunteer? Yeah, please.
Yeah, it's a process in which we use known species location and try to find species environment relationships. And then we use those relationships to predict where the species is most likely to be found.
Yeah, that's pretty much right. Yeah. So if I use just a very simple words, it's just pretty much building a relationship between the field observations, whereas most time it's going to be a particular species, a bird or animal or insect, and relate that to the local environment where this particular species live in, right? And that particular example comes down to the key question about scale, the environment or the niche, which is ecology normally many times defined. So what is the good representation of the environment to support the presence of a particular species, right? So this question, let's just put it a little formally. If I have a coordinate I should call it X, where I find species, right? And this species may be abundant, variably. Somewhere has more, has less. Say the number of species is a function of location. That's all fair enough, right? Then I'll come to the question to say the expectation value. Yes, this particular species can be written as a function of its location, and the function of location has to be linked back to the environment of this particular location, which I use Z to represent. So I'm trying to build a map, right? That's pretty much a definition of a species distribution model. The presence, the abundance of a species has to be related to the environment, right? Now, how do we define this environment? How do I know if I have a species here, I draw a circle, how big circle is appropriate, right? And that's pretty much the question. So I have defined a function that Z X is a function dependent on sigma. Sigma is what? Is this shape of your circle or square, whatever you draw, right? And that has to be weighted as a function. I don't have enough space here. My failure, sorry. So it's yeah. So what it's saying is basically the presence of a particular species of here, it depends on a particular kernel you fit in the environment, and you try to make this kernel bigger or smaller, and try to see the effect of your final observation. So this is a function depend on the definition or the scale of this environment. And you build a model, so it's pretty much, I just use a simple Poisson equation to represent. This is very general. So key is here is to use a variable to represent the scale of environment. Actually, Giuseppe, this is something I found quite interesting. Remember, we did about this kernel density stuff. I didn't see this paper, but I found this paper also had a similar idea. So apparently, to appreciate this model, right, we need some basic understanding about Poisson distribution and the density kernel and the probability calculations. So that's going to be the talk I'm going to cover in the next leg of this lecture. And this is just an appetizer to help you to see the importance of scale and how scale connects to probability and statistics. So I have no more say here. If you have any questions, please raise your voice. If not, we call it a pause here. We come back in the next exact hour. No question? Okay, break. Gradually, I just use this
meeting is being recorded.
This time to point out in the chat box, I put 3 URLs for 3 papers. That's for next Tuesday. Okay, not for Thursday, for next Tuesday. I think people can still see it, right? Although I posted before the beginning of the class. Do you see it, Giuseppe, in the chat box?
Yes, I'm also going to upload to the usual syllabus.
Okay, so those are 3 papers. They are very short, productive. I hope in the next time on Tuesday, we have a more interactive discussions. So today I pretty much did a lot of talking, and because it's the first time we talk about papers. And all these papers, I think they're quite important, because they capture some very key and important themes in geoscience. So I hope you find time to read them through. That's why I put on next Tuesday, and we can discuss a little more. So in the previous one, I talk a lot about this paper for this time. I hope I didn't deprive anybody's opportunity to speak up. In case, I think I offer this opportunity once more, in case somebody wants to comment on some part of the paper after reading it. Anybody want to say something? If you want, just let me know. I think I can see you guys. If not, that's fine. Okay, so now I'm gonna move on to the interesting material. It's the theory of probability. So before I start, I just lay out this assumption again, because I'm not you, and we have a very diverse group. Some you may find this material are too elementary. Others may find this one challenging or some sort of new. So I'm trying to mix them, but if you are the very advanced one, try to help me, provide some feedbacks and work out a problem together, then we can move on quicker. Now, if you are the person who see this one first time or something relatively new to you, I'll try to also gauge my pace so that you can catch up. But please provide feedback. So that way I can understand where you are, where I am, and how we can pace the best for this class. All right, so probability theory. Yeah, let's start from very basic fundamentals. Sample space. What is sample space? Anybody still remember who have been through theory of probability? It's a collection of all the outcomes of experiment, right? So it's everything in the entire space is called the sample space. And on top of that, there's also something called event. Event is a subset of your sample space. So it's not all the outcomes, it's some of the outcomes. Now this is also important. The so important thing is about the probability function, right? What is the probability function? Probability function is a mapping from your event into a number. That's it. So that's the probability function. There are some axioms in the probability. For example, the probability has to be positive between 0 and 1. And the disjoint the events summed together has to be a probability of identity 1. Those are not, I think, self-evident. There are some propositions. Yeah, I would write something here. I also want to introduce my notation because I don't have space. So I write the one in the full format, right? So if I say the probability between two events, the union of these two probabilities equals to probability A plus probability B minus their joint, right? That's definition. But you see how long it takes for me to write down this relationship. So I introduce some abbreviations just for my note, and hopefully you get familiar with. So I don't use this P anymore, it's too much space. So I say this union is A plus B in bracket. So that's the probability of union. And the probability of A is just bracket A, B just bracket B, and the joint is just A, comma, B. So it becomes much simpler and fit in the space much better. Okay, I just use bracket to replace probability function and use plus to replace union, and comma replace joint. Okay, so that's the simple notation I have. Now, I'm going to write down the formula for conditional probability. Okay, so conditional probability is A given B the probability of A given B or conditional on B is a ratio of the joint probability divided by the probability of B by itself. So in other words, it's a repartition of your sample space. So all these things I hope you are familiar with and comfortable with. So I'm going to go talk about an example here. And I want you work out the example with me together.
Can I ask
Okay.
a quick question?
Yeah, please. Who have a question?
This is Sebastian.
Please.
I asked if you could quickly, I think you mentioned it, but what is the difference between the union probability and the joint probability? Like if you could.
Okay. Yeah, sure. So I have two events, right? A and B. So the joint is the overlapping part between these two events. It's called a joint. So this is joint. And union is if you have an event A, B, no matter the joint or not, I talk about the together. So the entire, maybe it's not a better, I would do a better drawing here. It's not best. So it's better to draw this way. There are two events, A and B. I want to count these events cover the whole space, and the joint is only the overlapping part. Does that make sense?
Yeah, thanks. The drawings are really helpful.
Yeah, all right. Okay, so let me, because we already used up all the space right here, I'm going to just use an example to illustrate the calculation of these probabilities and also related to the independence, because independence is very important in geoscience. Okay. So I say the probability of rain, okay, on Friday, I'm sorry, on Saturday, it should be 6. Equals to the probability of rain on Sunday equals to 0.5. Okay? And the probability of 2 days, rain in 2 days in a row, is 0.6. Now, given these conditions, I want to ask you the probability of rain during the weekend. Because how much? Somebody can help me? So it's my notation, Saturday, Sunday, probability of rain on Saturday equals the probability of rain on Sunday equal 0.5. And the probability for 2 days to rain in a row is 0.6. So what's the probability to rain in the weekend? Let's just use the convention. One weekend has 2 days, Saturday and Sunday. Anybody want to give a attempt?
I could make a guess.
Yeah,
Yeah,
go
go,
again.
Sebastian.
Go, please.
If it's independent, then it would be 0.6, right? So maybe it's independent.
Well, I didn't say, yes, that's a good point, but I didn't say it's independent. Okay, the only thing I say
but
here,
this would be my guess, that because the probability for 2 consecutive days is 0.6, it shouldn't matter if it's on Sunday or Monday or Wednesday.
yeah, it doesn't matter. Just 2 days in a row. Okay, it can be
right.
Saturday, Sunday, Friday, Saturday, Sunday, Monday. 2 days in a row. That's all I said. Yeah, but it's a good observation about independence, because I won't go to the next example talking about independence. You're touching a good point, but this one I didn't say it's independent. So everything I laid out here just is given. I didn't say independent now. It's your own judgment. Okay, let me walk through maybe as the example together with you. Okay. So what are my interest is the Yeah, okay. So yeah, the question is the probability to rain during the weekend. So that means it can rain one day, say Saturday. It can rain Sunday or Saturday and Sunday, right? So all these possibilities are in there. So what I'm asking for is the probability of union Saturday and Sunday, right? That's all the possibilities. It doesn't matter what kind of combination you have, as long as it rains, if satisfy the condition, it rains on the weekend. It can rain on Saturday, rain on Sunday, or 2 days together, I don't care. So that's the probability. Now, how to calculate this one? We showed previously the equation for the union is 6 plus 7 minus 6.7, right? That's we have before. It's the probability of a Saturday plus Sunday minus the joint of Saturday and Sunday. That's the by definition. Now, how do we calculate this probability? I think Sebastian comes a very good point. What's the probability that rains Saturday and Sunday? That's the conditional probability, right? What it means, that means if it rains on Saturday and it rains on Sunday. So that means the conditional probability times the probability of Saturday. That means 0.3, 5.3. Right? So this is a conditional probability definition. I just read it. If you just remember the conditional probability definition is the conditional probability equals to the joint divided by this probability being conditioned now. Right? Then yeah, then it's pretty much it. And it's 6 plus 7, which is the union, equals 1 minus 6, 7 joint is equal to 0.7. Right, but it's important. It's important now to illustrate is these two events are not independent. That's why you have 0.7. Now I'm going to go right now into the concept of independence. If Saturday and Sunday independence. So what do you mean by independence? How do we show two events are independent in mathematically? Okay, I'm still here. See? Okay, still here. Let me just erase this one so we have more space. I want to write two equations, one on top of each other, just for comparison, right? Okay, so before we say the joint. The joint of two events equals to the event A plus event B minus their union. I'm sorry. The union of two events, I'm sorry. The union of two events equals to individual probabilities minus their joint, right? Now, if two events are independent, okay, this is a union. Also, the conditional probability. What's the conditional probability? Is the joint divided by the probability being conditional. So that's the conditional probability. These are very useful. These two equations are super useful. So now I'm going to introduce concept independence. So if the joint probability of a particular event equals to the probability of themselves, that means these two events are independent. You see the relation here? You see the interesting? So if you put this one back in here, you see, if two events are independent, That means it's the simple multiplication of the two events. You put back in here to the numerator. You get what? I just put back here. If I put these equations independence back into the conditional, what you got? You got does it make sense to everyone? Because two events independent, it's just simple multiplication, and you put back in the numerator, you cancel the b, you only have a left. That means if two events are independent, the conditional probability equals the original probability.
Sorry,
Okay,
I have
so
a question.
Yeah, please.
The conditional probability, is that a pipe operator, like a vertical thing,
No,
or
it's not.
is
It's not a.
is that
No,
a
it's not a
slash?
logic operator. It's just a mathematical notation. So that it
Yes,
only
but the
means,
notation, is that like the pipe operator sign? Is it a
yeah, it's a
vertical?
pipe operator sign. Yes,
Okay.
correct. It's just a vertical bar.
And, okay, and the one on the third line, the first, that's the comma, right? That's
Yeah,
like
I use a
joint.
comma to say it's joint.
Yeah, okay.
But the official one should be like this. But also, mathematicians also use.
Yeah, it's okay.
It's not something I created.
Thanks. Sorry
Yeah.
for the interruption.
Yeah, no problem. So I think this is very important for you to realize if two events are independent, and that means what? That means it change the calculation of your probability. Okay, now I bring back this same question as Sebastian already mentioned. If it's 2 days raining, still saying 0.5, then I say Saturday and Sunday. This is small notation here, like a one horizontal, two vertical. In statistical domain, it's called independence. If two events independent, Saturday and Sunday, so what's the probability of this 2 days rain? Yeah, during the weekend. That's just, I mean, Sebastian already mentioned that early on, right? In the beginning.
Should be 0.5, right?
Yeah.
Should be 0.5.
Yeah, that's just by itself. Yeah. So independent. Okay, perfect. So now I think we have achieved a lot. I'm going to have something really fun, but before we get that, I will introduce another concept. This one is also quite important. It's called the law of total probability. The law of total probability. Okay. So what it says is, if I have event B, the probability of this particular event, I can write it down as a summation of all the conditional probabilities. You see sub I here just indicate there are many small A events. That means the B event has been partitioned by A into so many pieces. It's like a pie, cut in slices. Okay, so now all the basic conditions I've laid here, we are ready to have fun. Okay, I have to write the table here. I hope you can see. Okay. I'll try to make it. So I have two groups. That's two group of patients under medical treatment. They have the problem of a kidney stone. Some of them have small ones, some have large ones. And I want to use this table to represent the effectiveness of the treatment. Okay. So this particular treatment for the small stones, they have a rate of recovery for 81/87. And this equals to 0.5. 93. This one for the large stone is 192 over 263 equals to 0.73. And this one, B group, 234 over 270 equals to 0.87. Then 55 divided by 80 equals to 0.69. So these are individually, okay? For group A, the small stone, big stone, their recovery rate, 0.93, 0.73, 0.87, 0.69. Now, if you look at it jointly, okay, together, the overall effectiveness, this is 0.78, this is 0.83. Now, it's my question. So if you look at this table, just by column A, the effectiveness of this treatment together, no matter small or large, is 0.78 together, right? Then if you like column B, no matter treatment small or large, it's 0.83. That means, based on the study of group B, the effectiveness, the overall effectiveness is 0.83, is greater than 0.78, right? But if you look at the small stone or bigger stone individually, if you look at the row, so the small stone in group A, they have more effectiveness than group B, right? 0.93, 0.87. And large stone is also group A bigger than group B. So you can see the two groups like different ages or different whatever categories. Then it becomes interesting, right? So if you look at the small big stone individually, you say, well, definitely this group A, you have observed better effectiveness of the treatment. But if you look at together, the overall effect of the group A is 0.78 and group B is 0.87. Is that reasonable? Does it make sense? I just gave here, I think it's not too big, but you have to trust me, it's 93, 73, 78, 87, 69, 83.
It's because of the different number of observations.
The number of observations, okay, can be a little more explicit. You're on the right track. It's very close. It's because different number of observations. But what kind of observation? What different numbers? Yeah, maybe they're a little small in fonts. I'm sorry about this. It's because the group A and then the group A and the group B, the number of participants have reversed attribution. So in group A, the total number of small stones is 87, large stones 263. But for the B group, the small stone have 270 and big stones is 80. So the relative ratio for each group changed. So it's a very famous statistical paradox. It's called the Simpson paradox. And you can explain this perfectly using the law of the total probability. So I already told you the answer. Actually, Aphrodite already told you the answer. It's about the disproportion allocation of different group numbers. But to really understand this, you just need to apply the law of total probability. So I'll leave this one as a homework if you have interest to do, or you can just Google it on Wikipedia everywhere. It's called the Simpson paradox. Okay, I will type in here in case. You can find it everywhere. It's a lot of examples. It's a lot of interest, but it all boils down to the law of probability. Okay, So now I think we don't have too much time because Giuseppe will come on quickly. So I think how much time I have? Only have 15 minutes. Wow, I have so much to go through. Well, let's get this. Yeah, I'll skip all these activities. I will just show the key results because we need this for next time. Okay, so I will erase this one for now. But anyway, we can have more time next time on Thursday to do these activities. Okay, so in case you have some interesting things, I really want to walk through with you with some examples, which is quite interesting. Okay, now it's Bayes' theorem. Okay, this is very important because I'm going to talk about this repetitively in the spatial modeling. It's Bayesian theorem. I think Aphrodite knows about it. Yeah, good. Okay, so basically this theorem is saying if I want to calculate the conditional probability of an event given another one, I can write this one as it's reverse divided by summation of this particular partitioning event. Okay, so Bj is a subscript just saying this B is not one event, it's multiple events. So the probability of a B event conditional on A is it's basically can be calculated as a ratio of the conditional probability of A conditional on Bj and take the summation. Summation is just a normalization factor. I hope we can see this clearly. And my question to you as a homework, if you have interest, is to show using the law of total probability to demonstrate this Bayesian theorem can be derived from conditional probability. Or you can collapse this particular formula into a simple conditional probability. So why is it useful? It helps you to understand what it means, because this equation here is a little dry. It doesn't really tell much, but it's going to help you if you derive this particular property by yourself. But I'm going to use a particular example to illustrate this concept of this Bayesian theorem. It's really much well known. Okay, so let's say there's a there's a 1% of a population have cancer for breast cancer for women, and 80% of the test. Okay, I see cancer, I say yes, this is easy. The test positive if this person has cancer. Now 9.6% or test negative, I'm sorry, test positive if it does not have cancer. So there's a false positive, right? Some people has cancer and test positive. Some people do not, but test positive. So this is 80%, is 9.6%. So now I ask you the probability of person to have cancer if test positive using the Bayesian theorem, right? So I will ask you to write out this by yourself, but I'll just write a result here for the simple, for the sake of time. So this is one, it's pretty much of what? Of the probability of a positive test result conditional on the person is positive times the probability of a positive person in the population divided by test positive of positive outcome and positive condition negative. That's the total probability, right? And the result here is about 0.48. So that means despite the testing outcome is 80% positive, each person is having a cancer, the conditional probability based on our theorem is that if the test is positive, the person has a cancer is only 0.48. So I will ask you to walk through this example by yourself. It's really help you to understand the Bayesian theorem, which is quite important in our analysis and calculations. So now I have not too much time. I won't talk about random variables, but I will probably just skip it for the moment. But I want to talk about one thing that's important, super important, is the expectation value. So what is the mathematical expectation of a particular variable? I will also use a funny example to work through with you, and I think that can stimulate some interest. Okay, it's the mathematical expectation of a particular random event. I use EX to represent. It's pretty much is the weighted average of this particular event and its probability. So this K equals to 1 to infinity. So it's a weighted average of this particular event as mathematical expectation. Okay, so why it is important and interesting? I will show you using an example, and it will be fun. Okay, it's an example about money. Okay, let's play a game. This is in my game. I see whether you want to be in my game or not. Okay, so this is the setup of my game. Okay, so this is me, and this is you. You hold a coin, and I hold a coin. Okay, each coin has two sides, head and tails. So I have these rules. If the rule is I flip a coin and you flip a coin. We don't know. We put on the table and look at the result. Okay, if after this flip, you have a head and I have a head, I gain $3. If I have a tail and you have a tail, I gain $1. On the reverse, if I have a head, you have a tail, or you have a tail, I have a tail, you have a head, I lose $2. Okay, so this is a simple game. Then we play this game, I don't know, as long as we want, for 10 times, 50 times, whatever. And under these conditions, do you think I can make a strategy that I will always win? Okay, first let's see if this game fair or not. So if I have two coins, right? The two coins flipping, the probability to see a head is 0.5. The probability to see a tail is also 0.5, right? So at the surface level, because you flip, I flip, there are two independent events. They are independent. So I don't tell you, you don't tell me. And the probability for me to have a head is 0.5. The probability for you to have a head is 0.5. So this is 0.5, 0.5 is what? 0.25. And this one is 0.25, 0.25, 0.25. So this is a $4. This is $4. The gain and loss is the same. right? So that's my setup. It looks fair, right, on the surface level. Aphrodite, you agree or don't agree? You want to play or not?
Yeah, let's play.
Yeah, play. So okay, so the result, you have to use the expectation values and to calculate if I can maneuver this game in a way that I always win. So what it means, I mean, when I say always win, I cannot say one time, right? One time is random. So long term, over a period of time, we do like 10, 50 times, I will win. Okay, Sebastian, you have a question?
Are you allowed to set the amount of money, or is that always the same?
Yeah, always is rules. Always is rules. The rules is the same. So if
No, I mean,
bet,
is it a fixed
okay,
amount of money you bet?
Yeah, always the same amount of money. Yeah,
Ah,
for
yeah,
each
okay.
for each round, okay, for each round. Yeah. So I cannot say it's not for one round. I cannot say I win in one round. It's not possible. Let's play 50 times or 100 times. You know, the statistics is over time, right? So I will tell you the idea to solve the problem, and I hope you'll find it interesting, right? It's about the conditional probability. So what do you mean I will win in the long term? So can somebody help me to translate this particular statement into mathematical language? If I say I will win over a long time, it's about expectation, right? So this time maybe I win, next time maybe you win, and overall expectation is saying I will win. So what that means? That means the expectation value is, for me, it's greater than 0, and for you, it's smaller than 0, right? That's mathematical outcome. It depends on from which perspective. So let's formulate this one from my perspective. I say, well, I don't have to, can I still see it here? It's a little small, okay? Let me just erase this one. I think top. Yeah, I think that's enough space for me. Okay, so let's say the probability, right? The probability, because you know I flip a coin I'm sorry, I flip a coin meaning that I have the control of this flipping. Okay, it's not saying I don't know how to flip. I put this coin in a way that I feel. In other words, I know it's going to be head or tail. And also do you. Okay, you have the control of head or tail, right? Maybe I may confuse you. Okay, so you have a coin and I have a coin. So each time I don't tell you which coin is going to be head or tail, but I know because I have this coin in my hand and I know how to control it, right? But we close our hand, put on the table, then we open our hand and see the result. So that's the game, okay? You have some control of this system. It's not just flipping by itself, because I say flipping because I'm going to illustrate this is a fair game. No, understand? So you have a coin in your hand. You can decide. You put the head on the top or the tail on the top. So do I. But I don't tell you, okay? And you don't tell me.
Yes, it's clear, Longzhu. But I
It's
think
clear, okay. Yeah.
I mean, if you put always head from your side, you have more chance to get a 3.
Yeah, but I don't have control of yours, right? If I
Yeah,
always
of
put
course.
head and you always put a tail, I mean, you always, if you always put head, then I win, right? But if I always put head and you always put tail, I lose, right? So that's the idea, because you also have control.
Okay.
Yeah. So let me just, because I know how often I will put head and tail on, because it's a long-term game. So my calculation is like this: the probability I gave head, you gave a head, is X, because I don't know. Your probability, I have no idea. The same here, the probability if I put a head over there, I also don't know, I see why, right? Now, I want to calculate the probability expectation of the probability of U. Or can the same calculate I, it doesn't matter. You know, U also, if U is smaller than 0, that means you lose, right? The probability of U is what? It's the probability of we have this particular situation, right? If I have my probability is Y and your probability is X, I gain 3 points, right? That's the calculation probability. If I put head and you put head, that's one thing. Then if I put tail, input tail, 1 minus X times 1 minus Y. So these two off diagonals, right? Then you have calculate diagonal, which is minus 2 X times minus Y plus Y times 1 minus X. Now it's a little time, but I think you can work out by yourself. What I did here is pretty much calculate the probabilities in all these 4 scenarios, because I don't know what you play and you don't know what I play. Now, this is expectation value based on equation, right? So basically 3 here, 3 times Y times X, because my probability to give head is Y and yours X, 3 times my X. And this tail, you know, the probability for head is X, then of course the probability of tail is 1 minus X, right? The same here, but probability of tail is 1 minus Y. So that's why you have 1 minus X, 1 minus Y here. On diagonal, one time I play X and one time play Y. It's symmetric. So now it's pretty much resolved. Okay, I just want to show you under this expectation, this calculation, there are certain conditions to make this one smaller than 0. And that condition will means you will lose. Because it's my game, I can control Y. Okay, so I don't know X. I don't care what X is. And I can control Y so that in certain conditions, this expectation value is smaller than 0. So this is going to be something you work out yourself. And I hope you will enjoy this one. And try to be careful if somebody want to play this game with you and see which direction you're going to take on game. Because there are conditions you will always lose. I think I'm almost at time. I didn't even get into the spatial part. Oh my God. Okay. I think I will. Yeah, I just briefly talk a little bit about the distributions. I think we all know about distributions. In spatial science, there are several ones very important: normal distribution, binomial distribution, and Poisson distribution. And in this species distribution model, the binomial is very common. So what is binomial? Binomial is a consecutive Bernoulli experiment, right? With Bernoulli, Bernoulli is like flipping a coin. It's only one experiment, only have 2 outcomes, head or tail. And binomial, it's pretty much flipping these coins multiple times. And you count the consequence of the result, the number of heads, number of tails. Okay, and this particular distribution is very useful when species distribution model, if you only care about in this particular area, you observe species versus not. And on the other hand, the Poisson distribution is about the counting the numbers. Let's say you are a ranger, you want to count deers in a particular forest. And you come out there and see on regular basis, the expectation value of seeing a deer is 2, okay? Just in over long-term observation, you only see 2 years in this area, on regular basis. Maybe today is 1, next is 5, but overall, on average, it's 2 years, the probability. Now then you ask yourself, what's the probability if you go out there, you see 3 years? What's the probability? So that's a Poisson distribution. So Poisson, binomial, and normal are very important in this class. Unfortunately, I don't too much time here to go through. Just please go through by yourself, just Wikipedia or something, or we can even allocate a little more time in the next class to talk about this. Now, the next one I'm going to move into is pretty much a linear model. Apparently, I don't have time today, but I think it's important for me to use time to consolidate this concept in probability, especially the models here, the Bayesian theorem. Please work out those examples if you found they are interesting, and we can talk about them more if you have an interest next time, or provide feedbacks. And today, I would say I conclude my remarks, and the very last leg will be Giuseppe going through the forest height example and just tell you the data preparation and the data distribution. Okay, so that's pretty much about me for today. Anybody has any questions? Okay, if not, let's break and come back in the next exact hour, and Giuseppe will be leading you through the forest height example. Bye for now.
Thanks, Longzhu. Yeah, it's record. Okay, so we will continue the lecture of today, presenting the data set that we are going to use from now on to try to combine all the information that we have done so far in terms of geocomputation and also in the TERFO modeling. So I'm going to present it today, because then later on, step by step, Longzhu and also Antonio, they're going to use this data set. So it's good to present it now in order to let them linking their theoretical application with a practical framework. Okay, we selected this data set because it's quite exhaustive, and it's also close to the field of geocomputation, and you can apply the same thinking for different kind of application, where you have always some observation this kind of observation. So in this context, so if you go under the study case, under the study case in our webpage, you can find the estimation of tree height webpage, where now I'm going to explain only the data set. So it's not going to be any kind of modeling, but just to present the data set and how we have been treating the data. So first of all, you can run this one is a quite big data set. It's 3 gig. I could not make it smaller, but also because we need quite enough data to show the machine learning capacity, the capability, and especially the plotting that was presented today by Longzhu, that was the modeling and the data. So we have the good area where we have a lot of data, and the complexity of the model has to be quite high. Over there is where you can see the maximum power of the machine learning. So in this context, you can run this line like always and get the last data set, not data set, the scripting, this one. Okay, then you can enter inside to the modeling tier, to the model that we always do it. Okay, then you can enter in the directory where we usually work. So at this point, you can run. I'm not going to run these two lines because it will take quite a lot of time. So I already did it. So if you didn't do it, you can do it later on. For now, you can just follow along the Jupyter, the Jupyter web page. So at this point, we have to do a little tricks in order to activate. And now I'm going to tell you. So this one is the usual source that we do it in order to get inside to the Jupyter Lab environment. When you enter into the Jupyter Lab environment, it's like you enter in a folder. Inside to this folder, you are going to install all your Python software. But there is also a way to use it, the Python library and package that are already native inside the OSGeo. And in this context, this information is stored in this file, okay? So this file, so now if I open this, is nothing else than a text file. So if you do perfect the same, you can see that you have included system setting package. In your case, is going to be false, okay? So if you do the same, you will see that yours is false. Due to that, I have been running already this line, set seed. I'm going to change in particular the false to true. And now, let's say the door from the internal Jupyter Lab environment to the external Python environment, that one that are native in OSGeo, is open. Okay, so we don't need to install it, all the Python package that are already there. Okay, so this is what is happening. And of course, this one need to be run only once. So from later on, we can just use it as it is the full system. So at this point, you can run these three lines. Pip install is going to install NumPy version 1.18 because it's needed by this library. Now I go to that. Then is upgrading the same another package. And again, you can run it. I did already. At this point, you can install the Gkit Gstart. So this one is the one that we use it in the end of the scripting procedure to see the spatial autocorrelation. So at that point, you can start the Jupyter environment. Okay. So I think I'm going to follow it over here without running, because sometimes the running, there are quite a good number of data sets, so it takes 2-3 minutes. So I'm going to explain the data set that has been already run, but feel free to run it by yourself, following or during or afterwards. So the JEDI dataset is the Global Ecosystem Dynamic Investigation mission, and the store is a satellite that is an instrument, LiDAR instrument that is stored on the International Space Station. Okay, so has been set like 2 years ago, so it's already 2 years that is sending and retrieving LiDAR information for different kind of application in the biomass. The LiDAR is nothing else that pools that arrive, like laser pools that arrive to the Earth, go back into the instrument, and the scattering return process and the changing of the wavelength and the time is able to identify the different length or the different height, where the difference between the heat and the ground back. So it's really calculate the distance. So these are pretty the same like the LiDAR that you always heard from normal drone system or airplane, but this one is a satellite. So it's a massive geodata set, extremely huge in terms of terabytes. So you really need, for a small study area, it's not a big deal. So like we are using, but if you want to start to process the full globe, and I have to say that I'm doing this kind of analysis, so it's really a massive combination of computational resources in terms of size, in terms of computational power, in terms of capability to work with all the tools that we have been using. The JEDI dataset is stored in the HDF5 format. So this one is a raster format, a sort of raster format. It's called, can be also raster, let's say, but in this case, it's nothing else. The table is stored in table. So it's so-called hierarchical data format. In hierarchical because together with the netcdf, they have an internal structure that you have. That's why hierarchical, because you have sub-layers inside, okay? So there is this JEDI subset Python code that is able to get this HD5 dataset and transform it to TXT. So this is an operation that I already done by some tweeting of this Python code that is available. You can go and link on the link, and you can apply this Python code, and you can retrieve the TXT file that you are going to use. So I also added some additional information in terms of data description of the data, because it's quite heavy in terms of also in terms of data set, inside data set and metadata that are inside to this HDF. So take a while to understanding how is structured the data set and so on. Feel free to go deep into the dictionary and the web documentation, user guide documentation, to see all the attributes inside this. And this one has been really a good achievement, because you combine the capacity to work with different tools in order to be able to run a study case. So these are the library that we are going to use it from step by step. So they should be pay attention that I'm not 100% sure that by this setting, all this one they are going to work, because I did several trials. So I'm not, but they should work. They should work. And if they are not, please also debugging a bit. Also because now I can do it again. So if you see some difference or some Python library that are not working, let me know and we can adjust it. It's more the library over here, the pip install tree and so on. So these are the paths that the JEDI is passing. It is covering almost all the Earth. In particular, is missing the, let's say, the topper part. The below, above 51 is not covered up. So all the Canada and the tundra area is not covered, or it's just partially covered. So, but it's very, very well present in all the surface of the Earth, with several passing during the day and during the night. So in this context, we are going to work in a small study case in north of Germany in order to retrieve the tree height. Okay, so in this context, each single beam that is called a laser beam can be recorded by two different kind of instruments on top of the JEDI instrument. And they are differentiated by the so-called coverage laser beam and full power laser beam. Okay, so each one of these points can be one of these. Okay, so these are all the stripes that we are going to use it. And for each one of these points, we are going to have several data sets, several values that we are going to see. Okay, so and in particular, whenever this point is representing one measurement, but in reality is nothing else than a set of different input that are ending in a 25-meter round. Some of these input, they're able to go through the canopy cover, okay, and hit the ground, but some other, like you see, they can hit the stem or the understory or just the canopy cover. So in this context, you can have a very huge profile of the different heat of the different input that are penetrating or not penetrating through the stem. So in this context, you can have different elevation height of the tree elevation over here, and the different number of inputs they identify the different RH 90 percentile, okay? So in this context, you will have the percentile, 5 percentile, where it is the one that is hitting the ground. And then you will have all the other percentile until you get the 95 percentile. So it's the most abundant one you can see. And they are eating all the full canopy cover. In other words, inside of this data set, you don't have just the height of the tree in the top, but you have all the different gradient in the height or in the tree height. You can really rebuild the biomass, the height, and so on, also the biomass of the tree cover. So there are several studies that has been used at global level, but also at local area to using this data set to retrieve the height and consequently also the biomass. So let's go through the data set that we have and that I have stored. And in particular, I'm going to explain each one of them and how I've been creating. Sometimes you will see the different aspects. And I will point to you how I've been creating all the different predictors and so on. So let's see before the text file that are stored inside to this directory. So inside to the tree height directory, that is the one that you should have after you do the unzipping. You should have, so this one is the one that you unzip, and then you have the tree height. So inside to this directory, you have all these files present. So over here, as you can see, we can already use it a bit of bash to list the file or Python code later on. So I always try to combine both of them to have a maximum flexibility, as I mentioned. So over here, we can see 6 different files, and you can see they start to count the number of row. And you can see bash with the command word count, WC, stay for word count. So you can see that already over 1 million points. Okay, so each one line is going to be representative of 1 point of this one, retrieving just the value of the 95 quantile. Okay. So, and let's go through one by one of these data sets in order to understand how I have been processing. Okay, so all these data sets, they come, just to repeat to you, they come from this JEDI subsetter Python script. So I'm going to use this one to retrieve this data set. But in order to having something already clean for the study case, as you can see over here, the study case, so the points are concentrating only on the forest area. Okay, so this doesn't mean that over here there were no points. So of course they were, but they have been already cleaning. So all the study area has been masked. You can see over here, has been masked out whatever is not forest. And whatever is not forest, I'm including all the urban area, all the agricultural area, and the water. Okay, so this has been done by setting by several operations of PK set mask and PK gut mask in order to completely get out of all the mask out, all the predictors, and concentrate my attention only on the forest area. Then the same operation I have done for the points. Also the point has been removed whatever was fell in the not forest area. So now one question for you, how I can remove the point that are fell in this one, for example? Just mention one of the tools. So I have points and I have one raster that tell me forest and non-forest. How I can remove the point? Make it simple. I have point location.
Is that an ignore value or like a no data value that's equivalent to the score for the forest?
Perfect. Yeah, considering the no data value. So considering if I have forest, no forest, 0 and 1, but how I can retrieve this information.
With GDAL location info, maybe.
Perfect, Aphrodite. With this file, in particular, I can use GDAL location info, okay, to run the full TXT file on top of my forest and no forest raster. And then I can retrieve only the forest point. So this point has been cleaned up, and I wrote somewhere here. I cleaned it up with running GDAL location info and removing whatever was not inside to the forest area. So again, we're going to use it, and also this is a point to point out to Longzhu and to Antonio that we are going to use it only points that are fell in forest area. Okay, so that's why I have given to you several files, more or less they include the same information, but some already are already clean, let's say clean, ready to be used. For example, this one ready to be used for GDAL location info. And as Aphrodite was dealing few days ago, or a few weeks ago, you can see there is no header, so is able to run immediately without any problem. Okay. So so this one you can plot it, and you can plot it by this line. You can read inside. One point to say, this rasterio is a Python package that is able to deal with raster file. Okay, so whatever we have been learning between in terms of GDAL translate, set mask, get mask, GDAL calc, you can do it also with rasterio. Okay, I prefer to enter in Python where all my data has been already cleaned up, cleaned and ready to go in terms of a pixel extent and so on. And pixel extent and also the size of the pixel and also extent of the study area. So this one has been treated again with GDAL translate, applying all the setting masking. In this way, you can see the same pattern all over the file. Okay, so then, so this is containing, this one containing X and Y coordinates in particular. Then there is one file that we are going to see if use it or not. Let's see how we are going to use it if we are going to use it inside the machine learning. That in particular is this one that is called X and Y select. Okay, 6 algorithm full table. And why is important this file? Because for each single point we have 6 algorithms that is giving to us the height of the tree. So it's not only one value, because also this one, you know, is a laser input. So the wavelet back and forward need to be transformed in meter, or actually this one are centimeter. So these is considered 31 centimeter. Has to be transformed in meter, in the height, and there are different algorithms. So different algorithms, in particular, there are 6, okay, that giving to us a different value. Sometimes very close, but sometimes they can be quite different. So, for example, over here, there will be like 20, maybe even more meter difference, okay? So all these information that are stored in this header are reported also here in this table. So now I'm going to run it through, and you can read over here.
Pepe,
okay. Please.
Quick question. So which algorithms are those exactly? I see that you're saying like 6 different algorithms, but what are they exactly?
So they are the algorithm that transform the laser input, return backward in meters. And of course, they are, I didn't run this algorithm. They already provide, the value is already provided inside to this HDF file. Okay, so in other words, each single algorithm has different function to transfer the weight that the bandwidth backward of the laser in meter. Okay, and each one of these has some drawbacks, let's say, or someone is better in some condition, some other, so they are providing all of them in order to get the best response if you want. I mean, if you want.
So each one of them has an error associated to the measurement,
Perfect,
right?
yes, perfect, very good. So
do you have that in the table as well?
So each one of them has an error, but we don't know because we still don't know the exact value of the tree height. Okay, but we have some kind of other information that can be useful for a better evaluation of getting closer as much as possible, selecting one of these that is more close to the real height. And in particular, this one is the minimum maximum of the one of these. I just calculated in order to have a data range between minimum and maximum. Of course, if these one are very wide, means that one of them can be really, really different. Okay, like over here, we have several. We go from 55 meter to 8 meter, so it can be very huge the difference, right? Rather, if they are very close, means that all the 6 algorithms giving to us the same information, very similar information. This other column is the beam, and in particular, you can go back to this
sorry.
Beam over here, yes.
Just before we move on, so we don't have real ground truth for this data, right? What we have is basically just like 6 different measurements, and we assume that the mean would be the best guess with respect to what's the real height, correct?
Perfect. We observe that is the mean as a first guess is the best one, but we can also throw away or not consider it someone of these algorithms based on some parameters that are located over here, because they are giving to us also some quality control and quality flag value that is helping us to select the best algorithm. Okay, so, and in particular, the beam value also giving to us information. So in particular, the beam is one of these. They can be coverage beam or full power beam. So, and in particular here, for example, you have the beam can have 8 values. From 1 to 4 is the so-called coverage beam, that is the worst. Rather, from 5 to 8, power beam is the better. Okay. So this one can already give into us, okay, I'm going to concentrate between 5 and 8. Am I using only the power, the power beam? So whatever is coming from this, I'm going to not consider in my machine learning algorithm. This one is giving to us the digital elevation model, the height of the digital elevation model. We are not going to use so much inside to in our computation, so you can skip this information. Then we can have quality control QC of the 6 algorithms. In particular, the quality control of the 6 algorithms can go 1 or 0. Okay, so for example, these one that are all 1, I could consider it all good, so I can do the mean of this one without worrying so much, let's say. But there are going to be someone or other that can be 0 or 1. So in that case, we can put some if condition to select the best one. Then we have another parameter that is the so-called sensitivity of the 6 algorithm. And this one is giving to us less than 0.95 is worse, and bigger than 0.95 is best. Okay, so also these information are going to give us a good quality control. So for example, over here, you can see that all of them are fine. All of them are good, bigger than 95, 98, perfect. So we can include all of them in the kind of average. Then we have another value, the degraded flag. In particular, the 0 is not degraded and is going to be good. And the bigger than 1, so bigger than 0, actually starting from 1 on, is going to be worse. Then we have last one that is during the day or during the night. In particular, bigger than 0 is worse, and less than 0 is better. Okay, so this one, for example, you can see that some are during the day and during the night can be selected. So far, I did, in order to create a data set that can be used directly by Antonio, I did just the average between 4 of these one, excluding the minimum maximum. Okay, in other words, I just did the sum of these minus these 2 divided by 4, and getting the minimum, the mean, without considering the extreme event. So I didn't create any kind of procedure to select this one. Okay, why I'm going to, I didn't do any, it's something that we can do it as a second step. So my intention is to retrieve as much as possible data to have a good amount of data to run a machine learning. Also because you can consider that if you see our study area, we are going to have the prediction everywhere where we don't have points. Okay, so, and due to that, the tree height is also really strongly influenced by soil condition, geomorphometry of the earth, amount of carbon, temperature, precipitation, and so on. More point we have, better it is. And in particular, if our error, if the error of the 6 algorithm is not so huge or is less than that our modeling error, then we are safe. So let's see if we can find some way of treating this data to have a better quality selection of the tree height. But so far, including all of them, so even here in this image, you can see all of them without any quality flag use. Okay, so I also calculate some statistics. So in particular, this one is quite with the GeoPanda. GeoPanda is a Python package for calculating some statistics, and someone is helping you to identify minimum maximum value of the 6 algorithms. So for example, this one is an overshoot. This is something that I would remove, cannot be a tree height bigger than 180. You know, bigger than 100 meters is very difficult. So this can be something that can be removed immediately. So that's why I created this statistic and so on. So for example, to give you a little bit of information, during the day we have 56, so 500,000, and during the night we have a bit more than half million. So this is something that we can use immediately. Okay, let's concentrate our attention just during the night. Okay, and over here I counted also how many degraded flag I can have for each single value. But anyway, this is something that you can play around, and is a combination. Here I was using yes, counting a number of, I just did it to show you how to use the Python package for counting, for creating some statistics and so on. So feel free to add in more of these line to understanding better the data set. So in particular, I prepare this data set. I prepared this data set. Oops. Yeah, this one I think I need to remove this one. So don't consider this. That is going to be just the average, like I mentioned to you, for each single of the 6 algorithms without considering the minimum maximum. So this is going to be our response variable that we can use it to plot and to extract different, and the X and Y to extract the different predictors. So let's see, first of all, which are the predictors that are being collecting for this study area and study case. So here you can see that I've been collecting, and you can go through each one of these, and they are below over here, and you can see the source. So I've been collecting, 4 different soil type files that are storing soil information, 1, 2, 3, and 4. Maybe we should. Then I have two files that identify climate condition, several ones that identify geomorphometric condition, latitude and longitude, and also satellite information that identifies some spectral difference. Moreover, we have another one that another 2 that identify soil temperature, so characteristic of the temperature of the soil. So all these data sets have been resampling and squared and rasterized, resampling at 0025 degrees. So this is sort of very close to 30 meter Landsat image. So this is the site of Landsat image, and have been plotting and cutting, as you can see, perfect precise on the digit level. Okay, so let's see the satellite image, how it's been treated. I calculate the spectral variability vegetation index. That is a combination between different bands in the GLAD-RT. So this is the same data set that I've been using in the temporal estimation. And as you can see over here, all of them have been masking out. So all the white area is the no forest area. Whatever you see in color are the forest area. So I also create histogram to show you immediately the range of the value for each single TIF. And this one is giving to you also some information about some outliers and so on. So this is something that can be useful, especially when Antonio is going to do some normalization of the data set. Is something that is good to have and explore in advance. These are the one for the climate data from the CHELSA data set. And also for this one, I collected 2 in particular. One is more temperature, yes, over here. One is more temperate seasonality, and the other one is monthly precipitation. Okay, so I collect 2 of these. You can see also here the histogram. Here are the 3 files of the soil grid. The 3 files of the soil grid. One is including more carbon content, the other one Gaussian exchange capacity in soil and bulk density. Then there are several geomorphological data obtaining for a data set, the geomorpho 90 meter, that have been developed 3 years ago. So in this context, we have different convergence of the terrain, northness, eastness. So it's given, and the deviation magnitude that is a roughness index. So all this information, as you can imagine, can give you information about how much sun is arriving, especially between the northness and eastness, and the concavity and convexity is giving to you the information about how much soil is going to be accumulated, and also how much water is going to accumulate in some particular places, so can help in identify the tree height. Okay, we have another tool that is more hydromorpho 90 meter. in particular the compound topographic index and the outlet distance. So the outlet to the distance. So it's how much the distance to the basin. So another last two are the so-called global soil bioclimatic variables that are identified the isothermality and the temperature seasonality in the soil. Then pay attention about this one. We have one file that is the so-called 3%, that is a value that goes from 0 to 100, where is giving to us the percentage of tree into the pixel. So completely 100% means that is completely covered pixel. So everything is a dense canopy forest, okay? So also this one, I suspect that is going to be a very good height in the estimation. And I've been using this, whatever was less than 0, I was considered like no tree, agriculture area or urban area. So that's one, this one was helping me also in identify the forest. Another one quite important that we are going to use it, and we're going to use it as an estimation that has been done, is this file, the forest height. This one has been developed, developed by this forest canopy 8 in 2019. And released as a publication in 2020 by a Maryland group. So, and they were using for this only satellite information, and I think satellite information and elevation, but they were not using any other environmental layers. So this one is the one that we will try to beat and getting better model accuracy. So remember, forest state is already giving us information height. So it's something that we will try to have a better value. Okay. So then I also calculate latitude and longitude to have information about the spatial variance in the lat long information. And this one I calculate inside grass using this command. So this one you can give the longitudinal gradient and latitudinal. So so at this point, when all the data set are being prepared, I run GDA location info with that file that I pointed before with the X and Y coordinate to get this huge table where I have, of course, my height, okay, coming from the average, just normal average, an ID that is helping me to identify the row in case I do some sorting. And then each one of these is, with the GDA location info, is the value of one point that is penetrating through all the pixels. So you can see that each one of these is the raster that I just mentioned out there. So one question that can come from your side, how you select this data set? Frankly speaking, I did in this way. I collect a lot of them. So for soil, there were like 20. For climate, there were another 20, and so on. Then I ran a huge random forest to have the variable ranking, and then I pick up the first 20. Inside these first 20, I try to pick up 2 for soil, 2 for soil temperature, another 2 for climate, another 3 or 4 for coverage, in order to reduce the amount of number also, because if not, the GDA will be too. So I did some kind of variable ranking before based on random forest. So I ran already a model with all these big number of variables, and they come across the most important one. So we are going to see how Longzhu and Antonio are going to use this data set to do the model. So below you can go by yourself, but I did the typical variable, exploring variable, where I compare and correlate the elevation versus, in this case, lat long, or elevation versus each one of the variable, okay? And you can see that most of them you cannot see, so the elevation is always the first one. So you can see that the linear model, there is not a real clear pattern. So probably if you just use it multiple regression, this one you will not get in very, very low accuracy. So that's why it's the beauty of machine learning that can deal with this kind of data. So feel free to go through this one and you will see the difference, and Antonio can point also the technique of variable explanation. Yes, Antonio.
Question. So you just described that you also did a filtering of the predictors, right? Based on the random forest importance score?
Yeah.
Correct. Are we also going to make available the raw data? Because maybe that would be like a cool assignment to give to the students, is to perhaps use a different method.
There is a very big data set. So
how many predictors you have in total?
100, something like this.
Okay.
Now and there are 20 something, maybe a bit more than 20.
Yeah, 20. I think the last one that you shared with me had 21.
Perfect, 21. Yeah. So but
yeah,
before they were much more. They were around 100.
Okay. Yeah, because I don't recall exactly how random forest gives the importance of the variable. Like, I don't think it's a gradient based approach, right?
Maybe Longzhu can say something about this. So I mean, I just use it the ranking, and I pick up the first step, you know, just to remove something, because I could not do 100 giga for the study case. But we can see how it goes, and we can see some model are important or not.
Okay. Yeah. I just wondering, like, if you use a different approach to select the importance of the features, like the predictors, right? If you're going to end up exactly with the same features, like if you use a different method, you know, like, so for example, one of the things that I'm going to cover is exactly feature importance via neural networks, you know, like, just to have like a parallel to what usually you do in random forest, right? Because that's something, it's very insightful to see what's the score of importance and like in which direction that specific variable takes you, right? To like a higher or lower estimate of a specific variable, like the tree height, right? So these kind of things, they are very insightful overall, like with respect to the works of the network. So, but I know that like in neuronal networks is like a gradient based, right? So like I change a little bit the output, and then I see how that change in the output impacts like estimate of the inputs, right? So basically you just reverse the order of the analysis. But I don't know how random forest does this kind of estimate, the importance of a variable estimate. I was just wondering if you guys...
we can read about it. Yeah, we can check it out. Anyway, also for the others, they are available, all the data set. If you want, I can share with you, and you can even plot in, and I can even share the scripting procedure that I use it to masking and to have all of them really under the same system. And also because, as you can see, and you will see, there are not so much the statistic of the table, and in particular this one is also helping you to identify some potential outliers, especially in the minimum maximum. So this one is very huge, but it's normal. The CTI is very huge. So but this one is also good. You cannot see so much at layer because the data has been treated very well before. If not, over here you will start to see no data value, -33 and -99 inside this one, and so on. So this is something that you need always to take care of before entering into the model, to have something really, really clean. Okay, we overpassed it a bit today, so feel free to go through and run it, this data set, to try also to improve it and get familiar as much you can with the data set, because they are going to be used quite intensively by Longzhu and Antonio, so it's good to have a good feeling of the data set of this. So if you have any question, you can resume.